Pressure forces are the P in VPIGs. So we need to almost always think about forces due to pressure in our flows. Fluids are hydrostatic at rest. That means that the pressure forces must balance with gravity if the fluid isn't going to go anywhere. So if I have a pressure like this acting on this side, there must be a balancing pressure like this acting on that side. Likewise, as the distribution goes down the sides here, the pressure forces balance each other, so there's no acceleration in the x direction. And you'll notice that the pressure is a little higher as we go down because we're a little further underwater or under whatever the fluid is, and the pressure's increasing hydrostatically. So there's a lower pressure on top here and a higher pressure on the bottom. But if the fluid's at rest, these pressures must all balance out. They balance out side to side. This higher pressure on the bottom doesn't balance with this lower pressure on top, except once you consider that there is a mass and that it is subject to gravity that's pulling it down this way. And that explains the pressure variation with elevation. So pressure forces, pressure's everywhere in a fluid, and that pressure is hydrostatic at rest. It has an arrangement like this. If we look at a system over here where we've got a box with some water in it, and this is the surface of the water, then the pressure will be atmospheric pressure at the surface, and it'll get higher and higher as we go lower below the surface. And that pressure will provide a distributed load on the sidewall of this tank. Now, sometimes it's expedient to treat that as if it was a point force acting at the center of pressure on the sidewall of the tank. And to get an equivalent force, it's got to be further down than the middle because the force, the distributed force magnitude, is higher down here at the bottom. Ideally, unless you really need to, keep in mind that this pressure force is a distributed force. It doesn't all act at a single point like this. Otherwise, if it did, it might punch a hole in a thin-walled tank, and it doesn't. Now, if there are unbalanced pressure forces, that will lead to an acceleration. So if we look at this system down here, we might have a pressure P1 on this side and a pressure P2 over here. And if P1 is bigger than P2, then this little chunk of fluid is going to accelerate in the positive x direction, this way. It's delta x wide. It's got a surface area of A here, and because it's a little square box, it's the same over here. So if we look at that acceleration, it's going to be equal to the ratio of force to mass. And the force, well, there'll be P1 times A acting in the positive x direction on this side, and P2 times A acting in the negative x direction on that side, so negative P2 times A. And the mass, well, that'll be the density times the volume, and the volume will be this area times this thickness delta x. So A delta x. The A's will all cancel out, regardless of what size this little box is, and we'll wind up with that acceleration equal to 1 over rho, the pressure difference, divided by the difference in distance delta x. And actually, P x, in this case, P is decreasing with positive x. It's a negative number, and that's where we get that negative sign. So this term is going to pop up later on in the Navier-Stokes equations, but it all comes back to this basic physics. If we have an unbalanced pressure force, then the acceleration that the chunk of mass that's caught in between those two unbalanced pressure forces experience is going to depend on the density and the local pressure gradient. So keep in mind, pressure forces, the second one in our VPIGs inventory.